In this video, we show how to solve the following type of question. Find a subset of some vectors. So I've given v1 through v5. They are vectors in R3. Find a subset of them that forms a basis for the subspace of R3 that they span. Now, there's more than one correct answer or one correct basis. Just find one. And then part B of the problem says, express each vector that's not in the basis you found in part A as a linear combination of the basis vectors that you did find. So the solution is that because our procedure for finding a basis for the column space of a matrix A returns a subset of the columns of A as opposed to the columns of the reduced row echelon form of A, which is the case for finding the row space of A, we form a matrix A whose columns are v1, v2, up to v5. So that's the first step. Take these vectors and make a matrix having them as its columns. So that's this matrix here. And then the next step is to figure out the reduced row echelon form of A and identify the pivot columns. So here's what SageMath returns as the RF of A. And I've circled the pivots. These are the leading ones in each row. And then I've highlighted in green their corresponding columns. So those are the pivot columns. That's what we'll need to remember, their positions. They're the first column and the third column. Sage starts again counting as 0, so when you type in this command, it returns 0 and 2. And then the next step is to go back to this matrix A and take those columns, the first column and the third column. So this column 2, 4, -8, and -1, 1, 2, that's going to be the answer for part A. So here's the answer to part A. These columns here, I've just written these columns as row vectors. You can leave them as column vectors, it doesn't matter. Okay, so then part B again said express each vector that's not in the basis as a linear combination of basis vectors. So one such vector that's not in the basis was v2, and we need to express it as a linear combination of the columns in green. Likewise, these two columns, columns 4 and 5, we need to express each of them as a linear combination of the columns in green. And once again, it turns out that we refer to the reduced row echelon form of A. And the key idea is that well, first of all, let W1 to W5 be the corresponding columns of the reduced row echelon form of A. So here, W1 is this first column and so forth. And the key idea is that the linear relations among these W's are going to give rise to linear relations among the columns of the original matrix A. That's a theorem we saw a few videos ago that says doing elementary row operations, even though they change the column space, they don't change relations between the vectors, the column vectors. Okay, so what are the relations between the column vectors of the reduced row echelon form? Well, they're easy to read off. So W2 is 3/2 times W1. So that's where I'm getting this. W4, that's this column here, is 2 times W1 because it has W4 has a 2 in the first position here, and then followed by -3 W3 because W4 has a -3 here, and W3 has a 1 here. So -3 times W3 will change this 1 to a -3 and give rise to this component, -3 here. Okay, and then similarly, W5 is 1 times W1 plus -2 times W3. So the point is it's very easy to read off from the reduced row echelon form the linear relations on the WIs. Those WIs, again, are the columns of the reduced row echelon form of A. And then we simply turn all these W's into V's. again, the V's were the columns of the original matrix A. And so, for example, this relation here implies that V2 is 3/2 V1. This one here says V4 is 2V1 minus 3V3. So we've expressed V4 as a linear combination of the basis vectors V1 and V3, and likewise for V5. So this is the answer here.